In this video, we're going to be looking at convergent and divergent series. We're also going to be looking at geometric series. Okay. Oftentimes with the series, we're interested in whether or not the sum of that series is converging or if it's diverging. That is, if it's leveling off to a certain number or if it's just increasing without bound. So we're going to explore that idea a little bit more in detail in these videos. All right, if you were asked to expand, okay, with this concise notation, okay, starting out with a sub 1, a sub 2 plus a sub 3. The summation notation just has us summing these terms. Plus dot 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 plus a sub n plus, and it increases. It's an infinite series. It doesn't stop. It's not finite. Okay. If an infinite series does converge, then we know that the sequence of partial sums approaches a limit. All right, so let's look at a sequence of partial sums to help us understand convergence or divergence. Okay, well, what is a partial sum? Well, S sub 1 just represents taking the first term and just saying, you know what? I'm going to approximate the sum of this series by just the first term. The second partial sum, denoted S sub 2, is just taking and adding a sub 1 and a sub 2. The third partial sum would have us add the first three terms, etc. The nth partial sum would just have us add the first n terms of the series. Okay, so this is a sequence of partial sums. All right, so let's look at a specific example and the sequence of partial sums with regard to that. For this specific example, I'm going to go ahead and expand and create a few of the terms. If n is 1, then I'm going to have 1/2. And summation notation means to add. If n is 2, I'm going to have 1 over 2 squared or 1/4. The exponent is increasing, 1 over 2 cubed, etc., which is 1/8, 1/16 plus dot dot dot. The upper limit, if you will, is going to be infinity, so it's going to keep going. Okay, so plus 1 over 2 to the n plus dot dot dot. So that's an expansion. All right, let's look at this sequence of partial sums. Well, we have to find the partial sums first. So S sub 1 is 1/2. And then let's add 1/2 and 1/4, which is going to be 3/4. The third partial sum would have us adding the first three terms. So 1/2 plus 1/4 plus 1/8. Okay, and getting a common denominator, that would be 8. When I collected, I would get 7/8. Now look at the fourth partial sum. So that would have us add a 16th. Okay, if you got a common denominator and added everything, you'd get 15 over 16. Okay, that's about it right there. I see the pattern. So what's the nth partial sum of this specific series? All right, and looking at this right here, this sentence, the statement, if this sequence of partial sums converges, the sequence of partial sums converges, meaning take a look at just, let's see if I can get a different color, take a look at just the answers here. Look at 1/2, look at 3/4, look at 7/8, 15/16. It's saying if this sequence, because I could create a sequence of these partial sums, if this sequence of partial sums converges, the series is said to converge and has the sum, and we'll write that down here in just a minute. All right, so I'm going to come back and look at this. As suggested by these partial sums, does it appear that these numbers, a half, 3/4, 7/8, 15/16, is approaching some leveling number, some limit? Okay. Well, it does to me. It looks like it's approaching 1. Okay. It doesn't look like it's going to get higher than 1 because if I just keep adding another fraction, it's just a smaller and smaller fraction that I'm adding. Like the next one would be 1/32. And you know, how small is that to add to this previous amount right here? Okay, well, we could do a little further work with this. I could say, let me come up with an expression, okay, for the nth partial sum. Okay, so if I looked at all of these values right here, okay, and kind of put my mind around, okay, well, what would the answer be? Because, you know, right here, numerically, we got a half, 3/4, 7/8, 15/16. What is this expression right here as suggested by this pattern? Well, it looks like a pattern to me. Okay, let's look at the denominator. 2, 1 is the partial sum number. If you have a 2 partial sum number, the denominator is 4. If you have a 3 partial sum number, the denominator is 8 here. 4, 16, etc. It looks like I'm taking 2 and raising it to the power of the partial sum, which is n. It looks like my denominator is just 2 to the n, whatever n is. Okay, but look at the numerator. Okay, if the denominator is 2 to the n, the numerator in each and every one of these fractions, like look at this one. If 16 is my denominator, my numerator is 1 number less than the denominator. Look at this comparison. 7 is 1 less than 8. 3 is 1 less than 4. So what's the expression here? Well, this right here. It's 2n minus 1. So this is an expression that represents the nth partial sum's answer. So, and if we find the limit of this right here, okay, and the limit approaches a number and doesn't go to infinity, then we can say that the infinite series converges. So I'm going to find the limit next. So the limit as n approaches infinity. So the more terms we add, that means n is going to get larger. So let's look at this. I'm going to put the minus 1 down here. Okay, well, what's that limit? Well, if I plugged in infinity, I'm going to get the indeterminate form infinity over infinity. So I can use L'Hopital's rule. So I'm going to find the derivative. So the derivative of the numerator, well, that's an exponential function. So its derivative is itself times the natural log of the base 2. The derivative of minus 1 is just 0. And the derivative of 2 to the n is the same thing I have on top. I can simplify now. This is going to simplify to 1. Ooh, the pen's not behaving. Okay, and if that simplifies to 1, then the limit as n goes to infinity of just the constant 1 is 1. Oh my goodness. So the limit of the sequence of partial sums exists, okay, and it's equal to 1. So that means that there's a sum of the series. If this sequence of partial sums converges, the series is said to converge and has the sum a sub 1 plus a sub 2, oh my goodness, plus dot dot dot, oh my goodness, plus a sub n plus dot dot dot. It's just telling us that there is a sum. And the limit S is called the sum of the series. All right, there's two main objectives of these notes, and one is, okay, does a series converge or diverge, and then also to look at a geometric series. So let's go ahead and take a look at that real quick. A geometric series could be of this form right here. A geometric series is just created by taking and multiplying preceding term by what we call a common ratio to generate the next term, and then do the same thing again. Okay, you're creating a geometric series by multiplying a previous term by what we call a common ratio, always multiplying by the same number to produce the next term. Okay, so what you could do right up here is you could expand a few of these, which we'll do down here. But convergence of a geometric series with ratio R, sometimes called a common ratio. It's that multiplier that generates the next term. A geometric series with the ratio of R diverges if the absolute value of R is greater than or equal to 1. It converges if the common ratio is a number between 0 and 1. Okay, so let's take a look at the expansion here. So if n equals 0, my exponent is 0, then r to the 0 is 1, my first term is a. We're dealing with the series, so we're going to add. If n is 1, then the next term would be ar. If n is 2, then we're going to have a times r squared, etc. So you notice that to produce the next term, you're always multiplying by the common ratio r. I think you've had earlier work with that too, a little bit in pre-cal and some in algebra 2. Okay, let's generate a few more terms till we get to the point where we're putting in a times r to the n plus dot, dot, dot. All right, so a geometric series with ratio r diverges if this is true, converges if the common ratio is between 0 and 1 numerically. The absolute value, then the series converges to the sum. I'm going to put it right here. There's a little formula we have to memorize. If you've determined that the series is geometric and its common ratio is less than 1, then the sum is going to be equal to the first term, whatever you get when you produce, expand, divided by 1 minus, not the absolute value of r, but just r. So if r happens to be negative, then you have to put the negative value in here. Okay, so at least we can find the sum of an infinite geometric series, which is kind of weird to know that you can find the sum of an infinite series. But apparently when you multiply by r and you get the next term, if you're multiplying by a half every time, think about the previous example. I mean, you're getting terms that are so small that when you add, to the previous partial sum, it's just not really having that great of effect on your sum. Okay. All right, so examples of convergent and divergent geometric series. Let's look at a few of those. Let's look at an example of a convergent and a divergent geometric series. So looking at this first example, okay, I'm going to try and get it to look, pretty similar to this format right up here. Okay, so I can do some algebraic things. I can rewrite it. My pen will work here. By thinking about pulling the 3 in front as a constant multiplier and having 1 over 2 to the n. Certainly nothing wrong with that. I'm trying to identify a and the common ratio. If I know I'm starting at n equals 0, like this formula here, okay, it looks like my a is going to be 3. My common ratio is the number I multiply to generate the next terms. I can still rewrite it. Oh my goodness. Okay, I can pull that n off of the denominator here and pull it outside and make this 1/2 to the n. Okay, so now we can see that r is a half and we have n as the exponent on this quantity right here. If you wanted to, you could generate a few terms. You could have generated a few terms from here, the initial problem, from here, the rewrite, or even from here. Okay. So if n is 0, I'm going to have 3 plus, if n is 1, 3 times a half, or 3 halves. If n is 2, I'm coming back to the first one, that's 3 over 2 squared, 3 over 2 cubed, 3 over 2 to the 4th, and so on. Okay, and so from this, any part of this at all, you can identify the common ratio to be a half. So it's going to converge. So it's helpful to know the a value which is 3. It's this first term. So if you were to add every single one of these terms up, you get 3 over 1 minus a half. That's just a half in the denominator. And 3 divided by half is 6. So the sum of the series is 6. I know it seems strange to think that, an infinite series is going to have a sum, but it does. Okay, let's look at this example right here. Okay, it's not quite in the format of this right here. I know that I start as an index at n equals 0. That's great. I need a first term here, an a value. It looks like the common ratio might be 3/2. We'll see. We'll see what happens. Yeah, I'm going to rewrite it. Well, the 3 is currently, and the 2 is currently busy with an exponent of n. Really, the only thing I can do is put a 1 in front here. That's it, just to show the 1 in front. Well, that's fine. That tells us what a is. Let's do an expansion, since I can't figure out how to rewrite it again. And let n be 0. Anything to the 0 is 1, so my first term is 1. N is 1, I'm going to get 3/2. If n is 2, I'm going to get 3 squared over 2 squared. 3 cubed over 2 cubed. So it looks like my common ratio is to multiply the top by 3 and the bottom by 2. My common ratio is 3/2. And that was visible right here. Okay, so what does that tell us? Well, these terms are getting larger and larger. The next one's going to be larger than the previous one, and if I have to go and add them all, well, if you keep getting larger terms, then you're not going to be able to reach some leveling number. So this diverges. And right down at the bottom of your paper, there's going to be a theorem, 9.7, properties of infinite series, on page 610. You might want to take a moment and look at that theorem. There's more than what I have here in the theorem, just a little more description, but it just boils down to there are a couple things that you can do with infinite series. Constant multiplier property, we have a sum and a difference property. So those are pretty important. We're going to be doing things with series, and we need to know the properties, things we can and cannot do with them. So they're found on page 610. All right, in the next video, we'll look at the back of this worksheet.